Think about how the DNA in a single cell contains the complete blueprint to build your entire body. Well, a function's derivatives at a single point are just like that DNA. These derivatives seem local, like they just give the function's height, slope, concavity, wiggliness, etc. at this particular point C. But hidden inside this single point is actually the complete blueprint for the entire function, even if we don't actually have a picture of the function itself. The question is, how do we extract this blueprint? How can we use this DNA to build the entire function step by step? The tool that lets us do this is called a Taylor polynomial, and in this video, we're not just going to use it, we're going to build it from the ground up. Before we start building though, we need to get our vocabulary right because precision here is everything. We're going to look at how to build a Taylor polynomial, which is a finite sum that approximates a function. We'll call it P sub n of x to indicate the nth degree Taylor polynomial. The difference between our real function and the approximation that's given by the Taylor polynomial is the error or the remainder, which we indicate with r sub n of x. In other words, we can say that the function's value itself is equal to the approximation given by the Taylor polynomial plus the error, or the difference between the function's actual value and its Taylor polynomial value, which means that if we rearrange this equation, we can write the remainder as equal to the function's value minus the approximation given by the Taylor polynomial. And sometimes our Taylor polynomial is going to be able to give us the function's exact value, in which case we talk about a Taylor series. In other words, the Taylor polynomial is a finite sum that approximates the function's value, and it includes only a finite number of polynomial terms, whereas the Taylor series gives exact value, at least inside a certain interval of convergence, when we take this value of n up here to infinity. In other words, we find the infinite sum, or the series, by evaluating the limit as n goes to infinity of this sum. All of this will become more clear as we go, but let's start by looking at why we can use an approximating polynomial in the first place. Think about a quadratic polynomial. We already know from algebra the form ax squared plus bx plus c as the general form of a quadratic. If we think about this as a second degree polynomial, which is why we write p sub 2, then we can use this as our starting point, imagining that it's going to be the foundation of our second degree Taylor polynomial. From here, to clean it up a little bit, let's replace the coefficients a, b, and c with a different set of coefficients c sub 2, c sub 1, and c sub 0, each of which matches the degree of each term. So we put c sub 2 with our x squared term, c sub 1 with our x to the first term, and c sub 0 with our x to the 0 term. Then we just change around the order. We reorder the terms by ascending degree instead of descending degree. And now, in theory, if we tried to use this approximating polynomial to solve for each of these coefficients, c0, c1, and c2, at x equal to c, the particular point we're interested in, we could do this, but what we'd end up with is a really messy system of equations. It would be clumsy, and the pattern we're looking for would end up being completely hidden. So what we'll do instead is use a more clever way to write our polynomial, and we'll recenter it around our target point x equals c. So what we say is that our function f can be approximated by this second degree Taylor polynomial, which is built from just the quadratic we're used to from algebra, ax squared plus bx plus c. We've just rewritten the coefficients, and we've replaced x with x minus c in order to center this polynomial around the point c that we're interested in. Now, this might look more complicated, but watch what happens to our coefficients when we try to force the values, slopes, and concavities of our function to match the polynomial one by one. So this is the approximating polynomial we just looked at, and we know from when we looked at notation earlier that this is the formula for a Taylor polynomial. The first thing we want to do is make the function itself, its value, at c, at x equals c, match the Taylor polynomial at x equals c. Because if the function's value and the value of the Taylor polynomial match exactly at x equals c, then we at least know that our approximating polynomial has exactly the same value at x equals c as the function itself, and so that's a good place to start. At the point around which we're centering our function, the values of the function itself and the approximating polynomial are equivalent. In other words, their graphs would pass through the same point. So if we plug x equals c into this equation here, notice that for these last two terms, we get c minus c, or 0. So this term goes to 0, and so does this term, leaving us with only c sub 0. So in order to get the values of the function and the second degree Taylor polynomial to match at x equals c, their values both have to be c sub 0. So their values, their heights, are the same, let's now try to make their first derivatives equivalent to each other. The way we'll do that is first by rewriting this approximating polynomial. So we keep the c sub 0, but then let's multiply this c sub 1 across the x minus c. That's going to give us c1x minus c1 times c. We'll leave the third term as it is. Now, remember, we're trying to get derivatives to match. So our next step is to take the derivative of both sides of the equation. So we're going to have f prime of x equal to the derivative of the Taylor polynomial, which is, taking the derivative of the right-hand side here, c0 is a constant, so its derivative is 0. The derivative of c1 times x is just c1. c1 times c is a constant, so its derivative is 0. And then the derivative here at the last term, we use power rule. We bring the 2 down in front to get 2c sub 2, and we subtract 1 from the exponent to get x minus c to the 1. Now, if we simplify that and our zeros go away, we're left with just c1 plus, and then distributing this 2c2 across the x minus c, we end up with 2c2x minus 2c2c. And remember, we're interested in the value at x equals c. So now we plug in x equals c, and what we get over here on the right-hand side is 2c2c minus 2c2c. So these two terms cancel out, and we're just left with c1. In other words, in order for the function itself and the Taylor polynomial to have matching derivatives at x equals c, the derivatives at x equals c have to be equal to c sub 1. Now let's do this one more time looking at the second derivatives. Remember, after taking the first derivative here, we got to this as the first derivative. So if we differentiate that to get the second derivative, the derivative of the constant c1 is 0. The derivative of 2c2x is just 2c2. And the derivative of the constant 2c2c is 0. So our second derivative is just 2c2. And if we plug in x equals c, well, there's no x value on the right-hand side here, so there's nowhere to plug in. And the second derivative at c is simply 2c2. If, however, we want to solve for the constant c2, we would divide through this whole thing by 2. And what we'd end up with is the second derivative at c divided by 2 is the value of the coefficient c2. And we won't continue to go through all the steps in detail. But if we were instead to be working with the third degree Taylor polynomial instead of just the second degree Taylor polynomial, we would find that our coefficient c3 has a value of the third derivative at c divided by, instead of just 2 that we got here for the second derivative, we would find here 3 times 2 times 1. And if we think about 3 times 2 times 1, we know it's the same thing as 3 factorial. And if we were to actually keep going with more terms in the Taylor polynomial, we would get the fourth derivative at c divided by 4 factorial, the fifth derivative at c divided by 5 factorial, etc. And what we realize is that we've had a factorial pattern all along. 2 over here is equivalent to 2 factorial. 2 factorial is just 2 times 1, or 2, so we can rewrite 2 as 2 factorial. For the first derivative, if we divide through by 1 factorial, c1 divided by 1 factorial is still c1. And for f of c, if we divide through by 0 factorial, remember that 0 factorial is equal to 1, so dividing by 0 factorial doesn't change the value of anything here. c0 divided by 0 factorial is still equal to c0. So we're able to apply that factorial pattern to every coefficient. And if we summarize what we found here, we can say that in order to make the Taylor polynomial and the function itself equivalent, we need to make their values at x equals c equivalent, their first derivatives equivalent, their second derivatives equivalent, their third derivatives equivalent, etc. And the way to do that is to make these coefficients, c0, c1, c2, c3, etc., always follow this same pattern, which is the kth derivative of f at c divided by k factorial. In other words, the 0 derivative at c divided by 0 factorial is c0. The first derivative at c divided by 1 factorial is c1. The second derivative at c divided by 2 factorial is c2. Or the kth derivative at c divided by k factorial is itself ck, c sub k, or what we call the Taylor coefficient. And so if we expand this sum, we see each of the coefficient values that we just found plugged into our original approximating Taylor polynomial, such that we have f of c coming from here in for c sub 0. We have f prime of c in for c1. We have f double prime of c divided by 2 factorial in here for c2. And we continue on with that pattern. That's how we get to our Taylor polynomial formula. We build it from the ground up from that original quadratic ax squared plus bx plus c. And now we can use this to find any nth degree Taylor polynomial And if we want the Taylor series, the infinite series, we just take the limit of this as n goes to infinity. And as we said, if we want the Taylor series, the infinite series, we just take the limit of this sum as n goes to infinity. What we have to say now is that that full series, the full Taylor series, is only going to be equal to our original function f on its particular convergence interval, and only if the function is analytic. But what do these mean? Let's talk about analytic functions. This is the function e to the negative 1 over x squared, and its graph, which you can see is very, very flat at x equals 0. A function can be perfectly smooth, meaning that it has infinite derivatives, and it can still not equal its Taylor series except at the single center point x equals c. Every derivative of this function at x equals 0 is exactly 0, so its series around x equals 0 is just 0 plus 0 plus 0 plus 0, which is the 0 function. But the function itself at x equals 0 is actually not 0, because you can see if we plug 0 into this function, in the exponent we divide by 0, which we can't do. So the moral is this: the Taylor series equals the function only when the function is analytic at the center x equals c. The good news is that if you're in AP Calc, you can safely treat the usual suspects, polynomials, rational functions on their domains, exponentials, trig functions, as all analytic functions. We just want to be aware that the Taylor series is only going to equal the function it's approximating when the function is analytic at the center point x equals c. Remember that our first caveat was that the function had to be analytic. The second was that it had to converge within a particular interval. Before we talk about that interval of convergence, we have to define a Maclaurin polynomial or a Maclaurin series. The good news is that a Maclaurin polynomial is literally just the special name that we give to a Taylor polynomial that is centered at c equals 0. Therefore, the Maclaurin series is equal to the Taylor series that's centered at c equals 0. We can center our Taylor polynomial or our Taylor series at any value x equals c, but when c equals 0, it's kind of a special case, and so we call it the Maclaurin polynomial or the Maclaurin series. Choosing to center our polynomial at 0 simplifies that Taylor polynomial formula because we get to plug in 0 for c, and that's going to simplify x minus c to the k to, of course, just x to the k. And now we can use this more simplified formula to build a Taylor polynomial centered at 0, also called a Maclaurin polynomial, around this special center point at c equals 0. In a second, we're going to use this to build a full Taylor polynomial, and then we'll be able to investigate our second caveat about the interval of convergence. But while we're here, let's also say that the Maclaurin polynomial for the exponential function e to the x is given by this sum here, and the exponential is actually special because it converges for all real numbers, the entire real number line, which means that we can rewrite it as an equality instead of an approximation, where e to the x is exactly equal to this infinite sum because it doesn't just converge for some small interval on the real number line, it converges everywhere, all the way from negative infinity to positive infinity. In fact, two other functions, the sine function and the cosine function, also have an infinite interval of convergence. They also converge everywhere for all real numbers. This doesn't always happen. Sometimes we get a finite interval of convergence, but all three of these functions converge for all real numbers. Let's dive in and look at how to build the Maclaurin polynomial for cosine of x, and then show that its interval of convergence is all real numbers. We're going to start by finding the fourth degree Maclaurin polynomial for cosine of x. And this is the set of steps we'll follow every time to find the Taylor polynomial or the Maclaurin polynomial. The first thing we need to do is identify the function itself, f of x equals cosine x, and then evaluate it at 0 because we're finding the Maclaurin polynomial. If we were finding a Taylor polynomial centered at, let's say, c equals 2, then we would find here f of 2 instead of f of 0. Because it's the Maclaurin polynomial, we know specifically we're looking at the center point c equals 0, so we evaluate at 0. And cosine of 0 is 1, which is how we get this value. And then we start taking derivatives and evaluating each of them at the center point c equals 0. So the first derivative is the derivative of cosine x, which is negative sine x, and negative sine x at 0 is 0. The second derivative is negative cosine, and evaluated at 0 we get negative 1. The third derivative is sine, evaluated at 0 we get 0. And the fourth derivative is cosine, evaluated at 0 we get 1. Because we're finding the fourth degree Maclaurin polynomial, we have to get up to the fourth derivative. Now we can start building our fourth degree Maclaurin polynomial. So we're going to say P4 of x is going to be equal to, and here we use that formula for the Taylor coefficient, where we say the 0th derivative multiplied by x minus c, or because this is Maclaurin, x minus 0, raised to the 0 power divided by 0 factorial. And we keep adding to that the derivative times x minus 0 to the first divided by 1 factorial, the second derivative term, the third derivative term, and the fourth derivative term. This is our general structure, but now we can start plugging in. F of 0 we know is 1. Anything raised to the 0 power here is 1, so we have 1 times 1 divided by 0 factorial, which is also 1. So 1 times 1 divided by 1, we get 1. So here we end up with 1. F prime of 0 we know is 0, so this whole term is going to go to 0. F double prime of 0 is negative 1, so we have negative 1 times x squared divided by 2 factorial, or negative x squared over 2 factorial. The third derivative at 0 we know is equal to 0, so this term goes to 0. And here we get 1 times x to the fourth divided by 4 factorial, or x to the 4 over 4 factorial. And if we put those three remaining terms, those three non-zero terms together, our fourth degree Maclaurin polynomial for cosine of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. That's what we saw in the previous section. And if we wanted to write this in summation notation, what we need to recognize is that now that we have the Maclaurin polynomial, we can call this the 0 term, the first term, and the second term. So for this term, k equals 0, for this term, k equals 1, and for this term, k equals 2. And so, turning this into summation notation, we could say that cosine of x is going to be equal to the sum from k equals 0 to infinity. And then the first thing we notice about our polynomial is that the signs alternate. We have a positive 1, a negative, and then a positive. So positive, negative, positive, which means we're going to have an alternating term, negative 1 to the k power, because when we raise negative 1 to the 0 power, we get a positive 1, positive here. When we raise negative 1 to the 1, we get negative 1, so we get negative here. And then when we raise negative 1 to the 2, we get positive 1, so we get the positive here. So we take care of the sign pattern with a negative 1 to the k. Then we notice that in our numerators, we have x to the 0, x to the 2, x to the 4 for k equals 0, 1, and 2, which means the way to take care of that x power is with x to the 2k. 2 times 1 gives us 2, 2 times 2 gives us 4, so x to the 2k. Same thing in the denominator. For the k equals 0, 1, and 2 terms, in our denominators, we have 0 factorial, 2 factorial, and 4 factorial, always double the k value. So in the denominator, we have 2k factorial, and that's how we write the Maclaurin series for cosine of x in summation notation. Once we have this in summation notation, then we can find the interval of convergence, which remember was the second caveat we said earlier, that in order for the polynomial or the series to approximate the function, it could only do so if the function was analytic and within the convergence interval. So let's look now at how to find that convergence interval. Think about the convergence interval as a trust bubble. It's our interval of trust, it's our bubble of trust. We feel good about using the Taylor polynomial or Taylor series or Maclaurin series to approximate the function inside that convergence interval, but only inside that interval. The way that we find that interval of convergence is using the ratio test, which tells us that we have to find this value of r, which is equal to the limit as n goes to infinity of the nth plus 1 term divided by the nth term, taking the absolute value of that. So this is the value of r, and the convergence interval is going to be given by r less than 1. So how do we find that? Well, remember, we said that cosine of x is equal to this infinite sum here in summation notation. If we didn't yet know that the convergence interval was all real numbers, then we would maybe say cosine of x is approximately equal to this sum taken out to the nth term instead of out to infinity here. But we're going to show here that this function does converge for all real numbers, which means we're going to be able to say that cosine of x is definitively equal to this sum taken out to infinity. So let's do this calculation for r. The first thing we have to do is find the n plus 1th term. In our case here, since we've been using k, that's going to be the k plus 1 term. And all we have to do is replace every k with k plus 1. So instead of negative 1 to the k, we're going to have negative 1 to the k plus 1. Instead of x to the 2k, we're going to have x to the 2 times k plus 1. So we replace all the k's with k plus 1. Then we divide that by the nth term, or in our case, since we've been using k's, just the k term. So this series, exactly as it is without changing anything, we're taking the absolute value of this big quotient and taking the limit of that as k goes to infinity. Now, this might look tricky to deal with, but it's actually not too bad because remember, when we divide a fraction by a fraction, instead of dividing by that fraction in the denominator, we just flip it upside down and multiply instead. So now instead of this big division problem, we've got a multiplication problem. And then notice that we have kind of matching terms across the numerator and the denominator. If we sort of pair those up, what we get is the -1 terms together, the x terms together, and then these factorial terms together. So we took the -1 terms, put them in their own fraction, took the x terms, put them in their own fraction, and then took the factorials and put them in their own fraction. Everything's multiplied together so we can keep the multiplication. And now this is pretty easy to simplify because, of course, exponent rules tell us that we can take this exponent, k plus 1, and subtract the exponent in the denominator. So k plus 1 minus k, the k's cancel, we're just left with +1. And so we have -1 to the +1 or just -1. Same thing here, we take 2k plus 2 minus 2k, the 2k's cancel, we're just left with 2, so we're left with x squared. And then over here, for the factorials, remember 4 factorial is just 4 times 3 times 2 times 1. In other words, every time we multiply, we decrease the number until we get down to 1. So 2k factorial is 2k multiplied by 2k decreased by 1, or 2k minus 1. And we keep going on and on and on. So 2k minus 2, 2k minus 3, 2k minus 4, or we just abbreviate that here with this ... Same thing in the denominator. We start with the 2k plus 2, but then we have to decrease that by 1 every time. So 2k plus 2, and then 2k plus 1, and then just 2k, and then 2k minus 1, and that could go on forever. What happens though, when we write that out, is that we see that we can cancel the matching 2k's and the matching 2k's minus 1, and we imagine that if we continued these on forever, everything past these terms would also cancel. So this 2k minus 2 would also cancel with the next term in the denominator. We also know that because we're taking this absolute value, this -1 is going to go away, and therefore, if we rewrite this, we recognize that all we have left is the x squared, and then what remains from our factorial fraction here. Notice that the limit only applies to k. We're taking the limit as k goes to infinity, which means that something that involves only x isn't going to be affected by this limit, so we can pull the x squared out in front of the limit. All we have to do is make sure that we leave the absolute value, and then we just have the limit as k goes to infinity of our factorial fraction. If we multiply 2k plus 2 by 2k plus 1, we end up with 4k squared plus 6k plus 2. And now things simplify really quickly because we realize that x squared is always going to be positive because no matter what value we square, a negative value or a positive value, the square is going to be positive. So the absolute value becomes irrelevant. We can drop it. And then if we apply the limit as k goes to infinity, this denominator is going to become infinitely large. And so we're going to have 1 divided by an infinitely large denominator. That means this whole fraction goes to 0. Its value approaches 0. So we end up with x squared times 0 or just 0 for this entire expression. In other words, absolute value of x squared times the limit as k goes to infinity of the absolute value of this whole thing, the value of this whole thing is 0. And remember, this value we just calculated is r. So r is equal to 0, which means that when we set r less than 1, we're setting 0 less than 1. And because this inequality is always true for all values of x, that means our interval of convergence has to be all values of x, negative infinity to positive infinity, or the entire real number line. And that's how we find the convergence interval for cosine of x and also prove what we already said, which is that the convergence interval for cosine of x is all real numbers. Now, the last thing we need to do, because we're going to need to know how to do this on the AP exam, is find the Lagrange error bound for our Maclaurin polynomial. So we already showed that the 4th degree Maclaurin polynomial for cosine of x was this polynomial here. What we need to know how to do is find the Lagrange error bound if, for example, we maybe use this polynomial to approximate cosine of 0.2. That's the kind of problem we might face. So first, let's just look at the value of cosine of 2 if we use the polynomial to approximate it. We plug 0.2 into our 4th degree Maclaurin polynomial, and the result, when we plug it into this 3-term right-hand side, is that we get about 0.980067. That is the value that this approximating polynomial gives us, which means that we think that cosine of 0.2 is going to have a value that's fairly close to this. The question is, how bad is this approximation of the actual value of cosine of 0.2? Well, the Lagrange error bound, if we calculate it using this formula, gives us a maximum value for the error, or it tells us how bad this approximation can be. When we find the Lagrange error bound, whatever value we get will be the maximum difference between this value we got from the polynomial approximation and the actual value of the function. So this formula for Lagrange error bound looks a lot more complicated than it actually is. What it tells us is that that remainder, or the error, can be no more than this value on the right-hand side. The first thing we notice is that we have n here in our formula. That refers to the nth degree Taylor or Maclaurin polynomial. So here we used the 4th degree Maclaurin polynomial, which means that when we calculate the Lagrange error bound, n is going to be 4. We also see that we have x minus c in this formula, and c, as it's been this whole time, is the point at which we're centering the function. And in the case of a Maclaurin polynomial, like we have here, c is 0. And then this big thing here at the front of the numerator, which is by far the most difficult part of calculating Lagrange error bound, is just going to be the maximum value of the n plus 1th derivative. So let's plug in the rest of this Lagrange error bound formula and then deal with this maximum value at the end. So here's what that's going to look like. The remainder, or the error, of the 4th degree Maclaurin polynomial has to be less than or equal to, in the denominator here, we have n equals 4 because it's the 4th degree polynomial. So we have 4 plus 1 factorial. And then, because we're approximating at x equals 0.2, we plug 0.2 in here for x. C is the center point. This is a Maclaurin polynomial, so c is 0. And then that exponent is still 4 plus 1. So this part is really easy. The only thing that's left is this maximum value of the n plus 1th derivative. Well, let's go back to our derivatives that we found earlier. Our original function here is cosine. Before, we took derivatives all the way down to the 4th derivative in order to build the 4th degree Maclaurin polynomial. So we already know all these derivatives, and the 4th derivative was the cosine function, which means the 5th derivative is the derivative of cosine, or negative sine. What we're saying then is that we're looking for the maximum value of the 5th derivative at z. Now, what's z? Well, when we use this Lagrange error bound formula, z always sits between c and x. So this formula is valid as long as z is between c and x. Well, in our case, c equals 0, because we have the Maclaurin polynomial, and then x, the value at which we're evaluating, is 0.2. So z has to be between 0 and 0.2. Now, normally, that means that we would need to figure out where the negative sine function is maximized between 0 and 0.2. But when we're dealing with sine and cosine functions, remember that sine and cosine always oscillate back and forth between -1 and 1. If we think of a sine graph or a cosine graph, and if this is -1 and this is +1, their graphs always oscillate back and forth between -1 and +1. So the highest value they ever attain is +1. The lowest value they ever attain is -1. And so regardless of the interval for z, no matter which interval we pick, the largest value that 5th derivative could ever possibly have is 1, which means that we can simplify this calculation and say that that largest possible value is 1. And then if we simplify here what we have, this calculation, 1 over 5 factorial times 0.2 to the 5th power, that's approximately equal to 0.0002667. And we're saying this remainder, or this error, cannot be greater than this value, has to be less than or equal to this value. And so the statement we can make then is that this approximation we found earlier, 0.980067, is off by, or differs from the actual value of cosine of 0.2 by no more than this tiny value we found here, which is the Lagrange error bound, which means in general that it's probably safe to say that this 4th degree Maclaurin polynomial is doing a really good job estimating the cosine function, because when we use this polynomial to estimate the value of cosine at 0.2, the Lagrange error bound tells us that our approximation, 0.980067, has to be within this tiny distance away from the function's actual value at 0.2. If this video helped at all, make sure to like and subscribe, and check the links down below for more help with Calculus 2 and AP Calc BC.